Welcome back, everybody. Here we have an example of oblique impact where the direction of velocity vector is not necessarily lined up with the common normal line. So we have two pucks as shown that collide obliquely on a smooth surface as depicted in the diagram. Knowing that coefficient of restitution E is 0.7 and duration of impact is 1 millisecond, we're interested in finding the final velocity of each object after collision and also the average impulsive force exerted on each puck during the impact. So let's draw a diagram to see how we can fill in the details of the equations. Here I've drawn two circles representing the pucks. Let's draw a line joining their center together. This is R plus R, which is 2R, assuming they both have the same shape and size. And then I can draw this line and make a right triangle. And then this helps us to see what this angle theta is. So if I draw the anti-coordinate system, let's show this line as the common normal line, and let this be t direction perpendicular to it. So this is the common tangent plane. So let's label this as t and label this direction as positive n. So observe that I have a right triangle whose opposite side is radius r, whose hypotenuse is 2r. If you recall from geometry, in a right triangle, the side opposite to an angle, if that is half of hypotenuse, the angle is 30 degrees, or I can simply write theta equals to inverse sine of opposite over hypotenuse. So this gives me a 30-degree angle for theta. And you see why I'm concerned about the angle, because if I show the velocity vectors, let's show velocity of this ball going to the left as this vector, and I want to redraw it, and the velocity of this ball is this vector to the right. So what we want to do is resolve these vectors along n and t direction to take the two components of conservation of linear momentum in those directions. Recall that is a vector equation. So what I want to write is this is V, let's call this ball B and this ball A. So this is VB initial equal to 3 feet per second, and this is VA initial equal to 6 feet per second. Excuse me. So if I continue with law of conservation of momentum, net momentum mv final in normal direction has to be equal to net momentum initially, so I write v sub I in normal direction, and I'm assuming this is the positive direction for this equation. Observe that both sides of the equation have mass m. Therefore, if I multiply both sides by scalar g, I can use weight instead of mass, and that makes it convenient as far as the numerical calculations are concerned. So let's say I multiply both sides by g, therefore mg equals to the weight. So I write weight of ball A, which is 5 pounds. Recall that pound is a measure of weight in mechanics. So that times velocity of A, final velocity of A in normal direction, plus for ball B, I have a weight of 2 pounds times velocity of B, final velocity of B in normal direction. That has to be equal to M, or weight of A initially is 5. Its velocity in normal direction is in negative normal direction because I'm choosing left and up as positive. Observe that normal component of VAI is right hand down to the right, so I should write minus 6 cosine of 30 initially, and then ball B has a positive momentum in normal direction, which is 2 pounds times 3 cosine of 30. I can simplify this equation slightly if I do the numerical calculation on the right side, and that turns out to be minus 20.78 with the appropriate units. Let's see, since I I multiplied both sides by 9.8, I should write that times G to be correct. So that's one equation of conservation of momentum in normal direction. Observe that in tangential direction, I can write a law of conservation of momentum for each ball separately. Therefore, for ball A, I can write velocity of A in tangential direction, final velocity equals to initial velocity in tangential direction. And that, if you look at the diagram, is, let's see, for ball A, this component is positive, so I want to write 6 sine of 30, which turns out to be 3 feet per second. Similarly, for ball B, I can write the same thing. Velocity of B in tangential direction, final velocity of it is going to be the same as VB in tangential direction initially. So VB is, if I draw it in T direction, is negative so much, so I should write minus 3 sine of 30, which turns out to be minus 1.5 foot per second. So at this point, I have this equation. I label it as equation 1. It has 2 unknowns in normal direction, therefore I need another equation with the same 2 unknowns in that direction. This is where I can use definition of coefficient of restitution. I write the formula here one more time, which is minus VA in normal direction, final velocity, minus VB normal direction, final velocity, and the denominator has VAN initial minus VB normal component initial. So that's the formula. If I follow the formula closely, I'll have, as far as numerical values are concerned, I have 0.7 for E equal to minus. The fraction has a numerator which has 2 unknowns, VAF normal minus VB final normal component, and then I have the initial velocities, so I plug them in numerically. For A, I have a velocity right and down, which is negative, so I should write minus 6 cosine of 30. This is a 6, not to be confusing, minus 3 cosine of 30. Observe that 3 cosine 30 is in positive normal direction for VB. So this is a second equation with the same two unknowns. I can consider equations 1 and 2 and solve them algebraically. So if I solve this second equation for velocity of A, final velocity of A in normal direction, I'll get 5.46 plus velocity of B, final velocity of B in normal direction. Plugging this into equation 1, so I want to take this, plug it in here, then I'll have one equation with one unknown. So let's go ahead and do the numerical calculation. Well, I was looking at equation 1 and observe that I already have used pounds for the right side of it. Therefore, I really don't need this G that I added in, so I erase it. Okay, so let's continue and do the algebra. Then I have 5 times final velocity of A in normal direction, which is 5.46 plus VB final in normal direction plus 2 VB final in normal direction equal to minus 20.78. Observe that this is a simple equation with one unknown. Therefore, I can do the algebra and find VB final. This is the normal component. It turns out to be minus 6.86 in feet per second, since the given values are in foot per second. If you look at the PDF solution, I think we might have made the mistake of writing the units as meters per second. So please make that correction. So at this point, I have this one unknown. I can plug this numerical value into equation number 2 and get final velocity of ball A in normal direction to be equal to, let's see, this is velocity of A normal component. So it is minus 1.41 foot per second. So I have both components. I can find the magnitudes, which is what we're after. Therefore, velocity of A, final velocity of A, total velocity is sum of the two components. So I want to take, let's see, 3 squared. This is for ball A. For ball A, I have this value squared plus this value squared. So I write 3 squared plus 1.41 squared, and this gives us a numerical value of 3.31 foot per second. If I do the same thing for ball B, velocity of B, final velocity is the square root of 6.86 squared plus 1.5 squared. So this gives us a numerical value of 7.02 feet per second. So these are both velocities after collision. Let's go to the next slide for part B of the problem. If I consider one of the two balls, let's say ball A, I can draw the diagram and show what's happening to it. Recall impulse momentum principle. Impulse momentum principle says that impulse of the force equals to change in linear momentum. So if ball A initially is moving in normal direction, I'll consider only forces in normal direction, I mean vectors in normal direction. So this is N diagram. Let's switch pen and call this N for normal. In this direction, recall that initially ball A has some initial momentum which is MA VA initial. Then what happens to it is an impulsive force acts on it in normal direction. So let's say that this is the impulsive force. An impulse of that impulsive force is Ft, where T is duration of impact and F is the average impulsive force, and that is in normal direction. Observe that in tangential direction there is no external force. So initial momentum plus impulse equals to final momentum. So I draw another circle representing the ball and show M sub A, I mean not mass times acceleration, but M sub A, mass of A times its final velocity. But I will only show that in normal direction. We already found the normal velocity of ball A after collision. So I'll show this vector as MA VA final. That's the normal component that I want to consider. Because I want to consider only normal component, observe that initially this is the initial velocity of ball A. So this velocity V A initial normal component, recall, is minus 6 cosine of 30, and we found final velocity of AVAF in normal direction as minus 1.41. I've shown it in positive direction, but in reality it goes left. So maybe I should have shown it in the way it is really acting. So this vector is really going in this direction. So I show it as it is really acting. So then if I write the equation in normal direction, impulse momentum principle, choosing this as positive, sorry, not that, but this as positive, then I have, let's see, M is 2 pounds divided by 32.2 times velocity initially in normal direction is minus 6 cosine of 30 plus Ft, that equals to the same mass of 2 over 32.2 times a velocity of minus 1.41. Recall that we found these on the previous slide. So if I rearrange the equation, this term goes to the right side, becomes positive, minus the negative term on the right side. So I can then divide both sides by a time of 0.001 seconds and get a force whose magnitude is 587.9 pounds. Note that in this equation, unlike what I did initially, I cannot use weight instead of mass because the second term Ft is force. I can't do what I did in the first slide. Alright, thank you for watching and we'll see you soon.